So good morning, everyone. Thank you for joining. So before I start, yeah, first a disclaimer. So whatever I'm going to talk about today is I'm not an expert in this topic, but it's been very fascinating because I did a small online course through Coursera a few years back. In fact, I think nearly 10 years back. That was delivered by Duke University. And one of the topics in that session, in that program, was the solar nebula theory. And it was very fascinating for me. So most of what I'm going to show you is from that courseware, but I redeveloped the slides and all that. And I did some online research on some of the aspects which I was not very clear about. So then I came up with this set of slides. That's what I'm going to share today. And um, and in terms of like no, you would see this Earth reimagined appearing at the bottom of the slide. So I launched this program a couple of years back, hoping that I can popularize astronomy, um, and I just wanted to take astronomy to public and school students, etc. But that really did not really work out. It's been right now limited to within my community only. And but my objective is basically to through astronomy, I just want to tell people that how fragile, lonely, and precious our planet is, and that's why I named this program as Earth Reimagined. And I do have a website. You can see it at the bottom of the slide. And please do feel free to visit my website. I do have few blogs, etc., written, which is posted on my website. So coming to the evolution of the solar system. So if you look at this part of the galaxy that we live in, and like no, we all know that the solar system was formed about 4.5 billion years back. So what was it before that? So what was this place all about? So where it all began? What was before the solar system existed? Um, like no. Where did it all began? Was it empty space, or was it a uh, like no? Is it again formed from another star, or it was formed from a nebula, etc., etc., right? So there are various questions that we need to answer. So but when we look up to the night sky, you see that it is so peaceful, right? There is hardly any disturbance, and you can see the stars twinkling, etc. But 4.5 billion years ago, it was a very different place. It was like the universe, as you know, cosmos is a very unforgiving place, and where violent birth and death is very common in terms of star formation and galaxies colliding, etc. So, so solar system also went through a similar kind of process before it reached this kind of a very stable state as we live in today. And so we'll just go through those the process of evolution of the solar system, and what are the pains it went through before it reached this rather peaceful state. So there were various different theories that were being proposed in terms of how this all evolved and how we reached the stage. So I will just start from that aspect. So there are three different models that were proposed in the past. One is a tidal theory. So this was the first two theories, that is tidal theory and the capture theory. It doesn't really address the formation of the sun as such. It expects the sun was already there, and in the tidal theory, a portion of that sun was ripped apart from the sun, and the planets were formed after the condensation of the gases that were ripped from the sun. That was tidal theory. Then capture theory was sun was already existing, and then it captured material out of which planets formed. So it basically captured material in the vicinity, and then for planets were formed out of those material. And the third one, which is most widely accepted today, is the nebula theory, which is a solar nebula theory. And it says planets were formed at the same time as the sun in the same gas cloud. So everything formed together, and that's how the planets and the sun came into being. So today I'll be only talking about nebula theory. I have not really tried to understand tidal theory and capture theory. So we will go deeper into nebula theory only today. So there were three key aspects of this theory. One is, of course, the role gravity plays. Like everything else, gravity plays an important role. And the second one is law of conservation of angular momentum. And the third one is condensation properties of elements and compounds. So these three factors played a very big role and vital role in the formation of our solar system. So we're all experienced astronomers, so I don't really have to explain this. But in a galaxy is basically made of stars and gas and dust. So like those gas and dust that you see is basically like we call it as molecular clouds, which basically comprise of helium and hydrogen, but there are traces of other elements as well in it, but predominantly it's helium and hydrogen. And some of the famous molecular clouds I just posted here in horse-fed nebula and pillars of creation, from where there are stars being born in these molecular clouds. So typically what happens is that in a steady state, people have been watching these molecular clouds, and the shape is pretty much the same. It doesn't undergo any change. So it's in a very stable state always. And but if something if there is any disturbance, which I'll talk about in the subsequent slides, then this steady state can become disturbed and then it starts collapsing. So there are 5 different steps through which this happens in the solar nebula theory. One is it starts with the spinning, and then it flattens the cloud, which was in a globular or in a different shape. It starts flattening, and then the heating happens. And then fourth and fifth is very, very important, and that's where we will spend most of the time in this session discussing. That is condensation of the elements and the compounds and the accretion of the disk. So as per this theory, a molecular cloud is basically in a steady state because of 2 different opposing forces. One is, of course, the gravity, which is trying to collapse it. At the same time, there is a hydrostatic pressure, which is trying to oppose the gravity. So this is a hydrostatic equilibrium. And so typically, this is not disturbed unless there is an external force acts on it. So in this case, this theory says that probably there is a supernova in the neighborhood that that happened, and then as a result there was a disturbance in this molecular cloud, or part of the molecular cloud. Molecular cloud is much bigger structure, but what we are talking about is where it all started was like a cloud fragment of size about 2000 to 20,000 astronomical unit. So those who don't know, astronomical unit is basically the distance between Earth and the Sun. So you can just imagine the size of that fragment that collapsed, and it had a mass of about 3,000 solar masses. So it's a pretty big structure that we are talking about. And once the collapse starts, basically the disturbance triggered the collapse, and then it continues under Newton's law of the motion and the momentum, etc., and the gravity. And as the gas cloud collapses, basically what is happening is basically it gets compressed, right, when the collapse happens, and the temperature rises because the potential energy, which was stored for so long and such a big structure, is getting converted to kinetic energy because of the collapse. And at this time, law of conservation of angular momentum kicks in. I have a small video, those who are not very familiar with this, which explains in a very simple demonstration how it works. And then once the law of conservation angular momentum kicks in, the temperature, density, and rotation rate increases rapidly so that it is conserved. Kicks in the temperature, basically the rotation, as the cloud collapse increases, the rate of collapse increases, the rotation increases, and to preserve that rotation, you have like, or the other way around, it's basically like your the cloud size of the cloud reduces, and as a result, just to preserve that angular momentum, the rotation rate increases because your r is reducing. So that is what is coming in the next slide, where you have this formula: L is equal to m into r into v. M is the mass, r is the radius, and v is the velocity. So typically, if you see a figure skater does something similar just to maintain the angular momentum. So if this figure skater wants to spin faster, basically she draws her hand towards her. As a result, the r is reduced and the velocity increases, keeping the mass constant. So something similar happens when the cloud collapses. So if you see the picture on the right side, so you have this molecular cloud, And so you have the, oops, I'm trying to use a pen. So the cloud is basically collapsing, right, in all directions. So what happens is that, so now it is rotating in this direction. So in order to maintain the angular momentum, it starts flattening, and it finally becomes like a disk with a central bulge. And so this is explained in. I'll just show you this video to make it easier to understand. You're able to see this video?
Yeah.
Okay, cool. So that was conservation of angular momentum.
Suresh, I have one question in the
So
quick
this,
slide.
yeah,
So one thing I couldn't understand here is, so when the cloud is collapsing, so how does it end up in
mhm.
a 2D or in a single plane where it was like a three-dimensional bigger blob of gas and
Because
yeah.
yeah, so in order to what do you call the when the so the collapse is happening in all direction, and the V increases because your R is reducing because there's a collapse happening. So initially it was like no, it was uh, a cloud of like no this size, right?
Hmm.
And then since gravity is pulling it inwards, the size of the cloud is reducing, and as a result, to conserve the momentum, the V is increasing. So the rotation speed starts increasing, right? And so what happens is that the centripetal force, so whatever is, so maybe it is better explained in the next slide. So what is happening here, if you can see my next slide. So the one, the basically the gas and dust in the periphery, right? It starts moving, honoring the centripetal forces. It will start moving in a what do you call
Circular
it
rotation.
starts rotating in this fashion, but the ones in the center, right, center of the axis of rotation, it starts collapsing because that is the only direction in which the gravity can exert, because this one is actually centripetal forces are pushing this, trying to like no as it rotate, it is trying to pull it inwards. At the same time, along the axis of rotation, the gravity is actually trying to push everything down, because gravity cannot bring everything closer to this side because of the what do you call the because of the angular momentum.
Hmm.
So this is a tendency. I actually there was a better video. I don't have it right now. Basically, it explains like no, when you're actually if you have a loosely made a ball kind of thing, and if you are like holding by a thread, and if you start rotating, that ball actually starts flattening.
Okay.
Okay, I don't
Okay.
know if anybody else in this call can explain this better, but this is my understanding that like no, because the gravity has to exert an inward pull, and since it's rotating, the one in the periphery will continue to rotate in that periphery, but the one in the center starts compressing downwards to the center, and it starts becoming like a pancake.
Okay. Okay. Got it.
It cannot completely become like a smaller ball of gas and dust, because the rotation happens, and to conserve this angular momentum, it has to flatten out. Because what will happen if, let's say, if everything starts moving to the center, right? So it has to like no, it has to the conserve the momentum, right? So if everything becomes small, then that this what do you call the conservation will not happen unless it flattens out.
Okay, got it. We have another question from Sudash. So he is asking that has magnetism got anything to this solar system formation?
No. There are two things. The condensation played a very big role, and then after the condensation, there is a process called accretion. Basically, initial. Okay, probably it is. Maybe I'm answering it a bit early. I thought I will explain that when we reach there. But in a short answer would be like uh, condensation ensures that gas cannot really stick to each other. So when condensation happens, it becomes like a solid or a liquid. Then it becomes easy for small elements and compounds to stick together to form a bigger object. And then as it grows in size, the gravity takes over, and then the accretion takes place because of the gravitational pull. So these are the two main steps involved in the final formation of this one. So magnetism never really played a role. And then of course, as you all know, magnetism is mainly because you have especially if you look at Earth is like a dynamo. There is a molten core and there is a mantle, which is so when the Earth is spinning, it is actually creating a electrical field. So that is how the magnetism is produced on Earth, because you have a molten core and you have a solid mantle. Whereas if you look at planets like Mars, it's already cooled down to such an extent that it doesn't have enough magnetism. So
Mhm.
magnetism is something that happened after the planet was formed.
Okay, I think yeah,
Hope it
that should
answers the
answer
question.
Sudarshan.
Yeah.
Yeah.
So I think this I explained. So I just read out. Collisions further flattens the disk. Gas moves in random directions and random speeds. Different clumps collide and merge. Original cloud thus becomes more orderly as cloud collapses, changing the cloud's original lumpy shape into a rotating flattened disk. So a lot of collision also happens across the axis of rotation, and as a result, it starts setting down into this flattened disk. So you can just see typically it's about 1 light year radius, the initial size of the molecular cloud, and it becomes something as small as 100 AU. So that is the kind of compression we're talking about. Vishwa, just to answer your question, your first question. So had it not become a flattened disk kind of shape, when does it stop? It has to continue compressing, and it will become such a small ball, right? So I don't know whether that is really possible, because it still has to um, there's so much of material, um, so that gravity may not be because of the rotation, that's a natural tendency to flatten out instead of becoming a smaller ball.
Yeah, I read it somewhere that I mean, just because that we are in a three-dimensional universe, the process of flattening will actually
Hmm.
explain that it is a three-dimensional universe and not any other higher dimension. Because so the collisions, whenever it is, I mean, trying to condense, right? The collisions cancel out in one
Hmm.
direction and only remain in one single plane. So yeah, that is a
Yeah.
eventual proof that
I
we are in a three-dimensional world. Yeah, but yeah,
Yeah, I
it
think
probably.
something similar happened for spiral galaxies as well. That's what I remember reading somewhere, saying that
Correct.
if you look at any spiral galaxy, there is a central bulge. So it's something similar to your solar system, right? So there is that central bulge is basically because of collisions, and then starts canceling out, and then it starts compressing in the what you call towards the axis of rotation.
Right. Oh, yeah.
I don't know about elliptical galaxies, but that's I don't know why the shape. Probably that rotation was not fast enough to flatten out, I guess, for ellipticals. Okay, let's move on to the third step, which is heating. So as gas cloud collapses, temperature rises as potential energy converted to kinetic. So the energy has to be preserved. So the heat increases, and and in this process, so there's a lot of concentration of mass at the center because of the compression happening along the axis of rotation, and that actually creates uh, uh, a lot of concentration of mass actually starts heating up that spot much more than the rest of the disk, and as a result, the proto-sun forms. This is basically the earlier form of the sun, like in its initial stage of evolution, and but it is still not started the nuclear fusion. That still takes some more time. But this is basically it's in the process of reaching that stage. Um, and then the third bullet point talks about the nuclear fusion. So protosun eventually becomes so hot that nuclear fusion ignited in its core. So that's when it becomes a T-Tauri star. So I will talk about T-Tauri star subsequently in the subsequent slides. And step 4, condensation. This again is the first stage in the formation of planets. So formation of planets requires seeds. So gas and dust cannot really stick together to form a planet like what we have. So it has to finally first condense so that it becomes smaller grains or smaller, slightly bigger seeds, which chunks of matter that gravity can eventually draw together. The process by which seeds were sown in condensation, when solid or liquid particles condenses out of a gas, condensation is temperature dependent. When the temperature is low enough, atoms, molecules solidify. So um, it's very important to understand the nature of condensation of different elements depending upon the kind of temperature in which it condenses. So subsequent slides basically explains that, and that played a very big role in how the different planets are formed. If you look at the kind of planets what we have Mercury, which is very, very solid, whereas we have, as we move towards the outer planets, the density actually reduces to some extent. Earth has got a molten core, and then there is a solid mantle, etc. But when you go to the outer planets, it's purely gaseous. It's got, of course, it's got a solid core. That's what people, the theory says, but it's more gaseous. So why it is solid in the inner planet, why it is gaseous in the outer planet, it all is explained by the process of condensation and what is available in which region of this disk that was flattened out. So what did this molecular cloud contain? It contained predominantly light gases like hydrogen and helium. 98% of this molecular cloud was composed of hydrogen and helium. And then you had hydrogen compounds like water, methane, and ammonia, which is only about 1.4 percentage. Then came rocks like silicates, that was about 0.4 percentage. And finally, other metals like iron, nickel, aluminum, etc., that was only about 0.2 percentage. So that's kind of composition this molecular cloud had. So now, if you look at this disk, the initial disk, so you had the central, this one protosun that was in the process of forming into a sun, and uh, and then you have this green line, which is basically the rock metal condensation line. So within this circle, the innermost circle, uh, everything was in a gaseous form because it was the condensation was not possible because it was too hot to the protosun. And whereas in the next outer layer, which is that bound the this greenish blue circle that you can see. So this layer had that's intermediate region which had rocks and metals are present in as frozen flakes. Hydrogen compounds and hydrogen and helium were present as gases. And so because it is slightly away from the protosun, and so the temperature was just enough for rocks and metals to be present as frozen flakes, and hydrogen and other gases were still in a gaseous form. But if you cross that light, that bluish green line, that is also known as the frost line. So this is typically our current asteroid belt, that is the frost line, beyond which things like water, methane, ammonia, etc., can exist in a liquid form. So it says rocks, metals, and hydrogen compounds are present as frozen flakes, of course, because it is still colder region. So those can still exist as frozen flakes. But these gases can also become condensed and become liquids. Um, okay, sorry. Hydrogen, helium are still gases, but things like water can exist in a liquid form. Whereas here, though we have a water, like though Earth has so much of water in a liquid form, that is purely because we have an atmosphere, so the pressure is maintained, and that's why Earth was able to sustain water in a liquid form. But otherwise, if you just take water outside of our atmosphere, it cannot exist in a liquid form. It can exist in a liquid form only outside this frost line. It's very important to understand this three layers because that's got a big impact or a lot of relevance on what we're going to discuss in subsequent slides. So any questions on this particular illustration? Okay. Um, if there are any questions, we can always discuss later. So continuing with the condensation. So if you look at this graph, so you have this is the frost line in the middle. Just before between Mars and Jupiter, we have the frost line, and as you can see, as the distance from the center of the solar nebula, there's a protosun, as it increases, the temperature starts dropping, and the your water condensation starts forming beyond Jupiter and beyond, and then Neptune and beyond, the methane also can condense to form ice. So inner planets, nebula temperature is greater than 400 Kelvin, made of silicates and metals, whereas outer planets, nebula temperature is not Kelvin, it's K. It's a temperature, um, I believe it is centigrade. Um, and nebula temperature is 300 K. I will clarify this later. I forgot what was it. Was it Kelvin or was it kilo temperature? I don't know. I don't recall completely. So whereas outer planets, you have nebula temperature which is slightly less than what it was in the inner region, and it is made of silicates and ices. Continuing with condensation, so this basically shows as we move towards the outer region, what kind of elements and compounds that we have in the planets. Like if you look at Mercury, you have aluminum oxides and iron, and then as we move towards Venus, it became silicates, and Earth is also, we have a lot of silicates, and then it becomes carbon-rich silicates. In the asteroids and Jupiter, then in this range ice forms, and then finally um, like you know uh, water in the form of ice, then methane in the form of ice. All that happens in the Jovian planets in this region. So looking at inner and outer solar systems, so within the inner solar system, we have the frost line. Within the frost line, only rock and metals can condense. Uh, there's a spelling mistake here. Planetesimals, therefore, made of rock and metals. It constitutes 0.6% of available material by mass. Inner planetesimals, therefore, grew more slowly and are smaller. So this is again a very important thing to note, is that um, what can condense within this region of inner solar system, and how much of material was available to form planets. Because if you look at this particular uh, slide, you can see metals and rocks were available in the inner planets, inner solar system, because I mean it was available in a condensed form. But the um, the amount of such material was very less compared to other lighter gases, etc. So the inner planets did not have enough material to form bigger planets. That's why we have inner planets in a smaller size compared to the outer planets. And since it did not have enough material to form, it also grew very slowly. Whereas in the outer solar system, beyond the frost line, the rock metals and ices also can condense. And planetesimals therefore contain these materials. It constitutes 2% of available materials by mass. So it had slightly more than what is available in the inner solar system. As a result, the initial formation of the Jovian planets, it still had the same kind of evolution as in the inner planets. But since the material was more in the outer planet, because the, the availability of water and methane, etc., was more than the other metals that were available in the inner solar system, it was able to grow faster and bigger compared to the inner solar system planets. And as a result, what happened? So when a body becomes bigger, the gravitational attraction that it has on other things will be much higher, and as a result, it was able to attract more hydrogen and helium, which is available abundantly in the molecular cloud, or the flattened disk rather. And as a result, it was able to grow much bigger and faster compared to the inner solar system. So, but the condensation, how it was done for inner solar system planets as well as outer solar system planet, which was pretty much the same. It is just the availability of material in the condensed form in the inner solar system was much smaller compared to the outer solar system. As a result, outer planets were much bigger, and it was able to exert much more gravity to attract lighter elements. I know it can be a bit heavy at this stage, so I can just pause for my minute, and I can take any questions if you have.
Suresh, I don't think there are any more questions, but I think I
Okay.
just wanted to, ask one additional thing. So, how does this explain the moons of Jupiter or Saturn? Because they are supposed to be a little bit rocky when compared to its parent planets.
Yeah. So if you see, this condensation is pretty much consistent across all the planets in the solar system. How the initial stage of planet evolution happened, it's pretty much the process was pretty much consistent in terms of the material in the molecular cloud has to first condense. That's the first and foremost thing to happen, and that happened uh, across the initial disk. But how much was available and what was condensed varied. So if you look at the inner part of the solar system, we still had same kind of material, but um, the rocks and silicates, etc., was able to condense only in the inner side because the gas was not able to condense because it was hotter in the inner region. In the outer region, you still had all these rocks and metals still condensing, and that's how even the Jupiter and Saturn and Neptune and Uranus, everything started in that fashion. But it's just that it had a lot more material available to condense, so it became much bigger and it started attracting. So even the moons of Jupiter, like Titans and Europas, etc., they also had the same kind of material available to condense. So that's how it became rocky. But uh, probably it was like no, of course, that like no. If you look at our own moon, it was not existing earlier, right? Then the theory says another planet called Theia came and had a head-on collision with Earth, and then a big chunk came out of Earth, and then moon was formed. So all this moon formation is completely different process in terms of when it actually happened. So as these planets, the bigger ones were growing, a lot of other condensation and accretion, all that's happening in the other regions of the solar system. And then like even today, if you look at Jupiter, it keeps pulling stuff, and then that becomes their moons. So because they're so massive, it has the capability of attracting other bodies, the smaller bodies, towards it, and it and that and those bodies becomes moons. If if Jupiter and Saturn were not around, probably you could have had more smaller planets. Probably Titan would have been a planet on its own, right? So, so what I'm trying to say is Titan did not become like a Jupiter because probably Jupiter took away most of the gaseous material available, like helium and hydrogen, before others could take it. So they were left with only those rocky materials. Does that make
Okay,
sense?
got it. So it's a similar process on
Yeah.
how planets around the sun formed. Similarly, even the moons around the Jupiter would have
Yes.
formed in similar way
Yeah.
when Jupiter sucked the lighter
Yeah.
elements.
So I mean, even Pluto was a planet till few years back, right? So even that is rocky,
Right.
but it's icy, right? So it's just that probably Pluto was too far outer into the solar system. So Jupiter and Saturn could not really exert enough pressure to make it a moon of Jupiter or Saturn. So probably it was saved by the distance from these planets. And towards the end, I will explain certain other interesting thing about all these Jovian planets and the kind of pressure and strain it exerted on other planets. It's very interesting, actually.
Okay. Yeah. We have one question from
Okay, I'll
Suresh.
move on. Yeah,
Uh,
yeah.
yeah. So, what is the rotational speed in these times, and how they changed during this evolution? Yeah. So, probably during the
Oh,
condensation,
okay.
what is the rotation speeds that we are looking at?
Yeah. So I was reading about it actually. So what happened was, especially if you look at Jupiter and Saturn, they rotate much faster than inner planets, right? So what it says is that because the growth was so fast, like no the accretion that happened after condensation, they were able to take up so much of material in such a short span. uh, the rotation speed was much higher because they had so much of material and this angular momentum had to be maintained, so rotation has to increase. So that's why they spin so fast compared to other planets. I don't
Okay.
know about the spinning speed of Uranus and Neptune. I haven't really studied much. Do they also spin so fast? I think it is still faster than the inner planets, I guess.
Yeah, yeah, they are faster than in inner planets, except for Pluto.
Yeah, it's probably that no, the amount of mass it accreted that had a role to play in the speed, just to conserve the momentum. Okay, so that was condensation, an important step in the evolution. The next important thing is accretion. So, uh, so once you have these condensation that actually creates small granules and smaller, slightly bigger kind of bodies, um, then it starts you have this kind of collision that's happening because it's all moving in random directions. They still have not really settled into their own Keplerian orbits. So uh, that's when this collision happens, and when it is a gaseous stage, it's much more freely moving. But once it starts building its size and material available within it, the collision becomes more rampant, and that's when the actual planet building process happens. So large particles formed from tiny contrails, about 1 millimeter in size, and porous particles held together by uh, van der Waals forces. So it starts sticking together through these forces. And these contrails are basically, what I was reading was like these contrails are basically slightly bigger in size, like 1 millimeter or slightly even bigger. And these are the most primitive um, things that we can study to understand the age of the solar system. So they do the carbon dating on this. I think what these contrails are basically made of aluminum silicates, I think, and these are even available even today on Earth. And they look at these silicates and then try to understand the uh, age of the solar system through carbon dating, because this is supposed to be for the most primitive of the material that actually eventually formed the planets, these contrails. There are some unanswered questions in towards the end. I'm going to explain those as well. There are some questions about these contrails as well, and this accretion then proceeds into two ways. Through geometric cross section and through gravitational attraction. So geometric cross section, if you look at typically if you look at snowflakes, right? Snowflakes, the picture here shown is basically a snowflake when it is actually magnified. So it's got all these kind of geometric cross sections, and it actually helps in holding everything together. So if you look at snow, you can make a snowman, and you have this avalanche happening mainly because everything is held together using this geometric cross section. And if that gets disturbed, and it starts falling down in the form of avalanche and all that. So something similar happened in the past, where these contrails had geometric cross section, and it was able to held together, or hold together rather, to form bigger bodies. And as this size starts increasing, because that more and more condules starts sticking together, and its size increases, and it's beyond a certain size, gravity takes over. And from that point onwards, accretion is completely driven by gravity. Gravity starts dominating, and it starts pulling more and more matter to it, and it starts sticking together to form bigger planets. Okay, so basically it is called planetesimals, the small bodies like our asteroids and those kind of bodies. and then finally gravity takes over and then makes it bigger and bigger to form the planet. So geometric and gravitational accretion in more detail here. So it coalesces into larger objects, few kilometers across in few million years. That is geometric accretion. Once planetesimals had grown to few kilometers, gravitational accretion dominates to form protoplanets. That is the planets before it is actually the body before it became actually planets called protoplanets. The biggest planetesimals grows the fastest because it's got more gravity to pull other stuff. Smaller planetesimals are quickly destroyed by fast collisions and turned into smaller fragments. So typically one object will dominate a region. So anything that was able to gather more material into onto itself through gravity grows much faster compared to other smaller ones. So smaller ones, if they're not able to gather more material, it will be destroyed through collision. And probably those are like the asteroids and comets that we see are those which could not become planets. Ultimately, one object will dominate a particular region, like or Mars or Venus or Earth, etc. Continuing with accretion, inner planets formed slowly due to small amount of metals and rocks. I already explained. Geometric accretion rate and gravitational accretion rate are small. T-Tauri wind blows away the gas and dust. So T-Tauri wind is basically like the proto sun that was actually forming while all this was going on. It gathers enough material to start the nuclear fusion, and that's when it actually becomes the initial stage of the sun, and that's called a T-Tauri star. T-Tauri is actually named after one of the stars they found in the Taurus constellation. That's how the name T-Tauri came in. One of the stars they found in Taurus constellation had this kind of characteristics. A young star. So typically, what we're talking about is something like a 10 million year old star. That's a T-Tauri star. And when the thermonuclear reaction starts or the fusion starts, the solar wind starts uh, propagating outwards, and that is a T-Tauri wind. And this T-Tauri wind blows away all the remaining gas and dust that could not become planets. So it's kind of a just clearing away all the debris left behind from this construction. So uh, it is blown away to the outer reaches of the solar system, and I'll just come to that. What happens with those are still not thrown away into the interstellar medium, but it is still around. We will just see soon what happens to that. In the outer planets, the so in the inner planet, a lot of this bombardment and collision, and it was much more violent compared to the outer planet, because outer planet it was more gaseous, and whereas in the inner planet it was more rocks and more solid material was available, and as a result it was more violent compared to the outer planet. And the great quantities of ice at greater than 3 astronomical unit resulted in large rock ice cores forming. I already mentioned that. So reason for rapid core growth is that ices have large cross-sectional area. So compared to other metals like your silicates and other things, ice, the cross sections were much more. As a result, it was able to stick together much more easily compared to other material. So that's what is explained here in the illustration here. So you have outer regions colder, more volatile, more mass, more large planet mass. So the ice crystals was able to stick together much more easy because it's got more cross-sectional area, and then finally it becomes a big planet. So just to summarize, so it starts with the geometric accretion, and then the gravitational accretion takes over to form planetesimals, and then more collision, etc., forms, and then it gathers more material, and then planetesimal becomes protoplanets, and then finally becomes planets. The final stage in the growth of terrestrial planet are dramatic and violent. Large mass-sized protoplanets collide to produce objects such as the Earth and the Venus. So even like I was talking about the planet, the Theia coming and bombarding onto Earth and forming Moon. So all this kind of bombardment happened in the evolution. So it was a very violent process. So all those planetesimals which could not become planets, where are they now? So most of them are stuck in the orbit between Mars and Jupiter in the form of asteroid belt. So asteroid belt is a resting ground for collision evolved planetesimals that were not incorporated into a planet. Total some numbers here. Total mass of asteroid belt is 5 times 10 to the power of 21 kg, which is about one third the mass of Pluto or 1/50 the mass of Moon. It's just numbers, no major significance to what we're going to discuss here. Ceres, the largest asteroid, has a diameter of 940 kilometers and a mass of 10 to the power of 21 kg. A planet probably did not form in this region because of the rapid formation and resulting large mass of Jupiter. So Jupiter and Saturn was wreaking havoc in this area, which we will see soon. What was happening in this area after it was formed. So these asteroids could not really become planets because of the existence of massive planets like Jupiter in the vicinity. Okay, so that is the orbital resonance I want to talk about. Before I talk about orbital resonance, let's look at a small video here.
Suresh, before
Vishwa,
we
how are
go,
we doing for time?
we are close. So it's almost 1 hour, but it's okay. We'll still continue till
Okay.
one, and we'll see. And there is one question from Sudash. So, is there a proportion in which star versus planet mass and size are formed? So, is there any proportionality, or can even planets in the outer planets, when they start forming, can they become bigger and bigger uh, than the sun itself sometimes?
Possible, because people say that Jupiter was a planet or a star that could never become a star, right? Because it had so much of mass and it's got so much of hydrogen and helium in it. It is a mystery that why it couldn't really become a star. Possible. Maybe that's how some solar systems have multiple stars, right? Binaries and all that. It's possible. But in this case, it all depends on, I think, the size of the molecular cloud that collapsed, the fragment, and how much of mass was available in the center, because everything is now falling towards the axis of rotation. And that's where the central bulge, and there's so much of material available in the center. That's why the sun is always in the center, and that's how it originates. But yes, maybe it's possible that Jupiter could have become a sun. But I don't know, Sudhanshu, what is the proportion? I haven't really checked that. But maybe that is something that we can park and then maybe discuss offline. Um, but I think if you look at the mass of Sun and mass of Jupiter, the Sun is still much, much bigger than Jupiter. So I think the proportion has to be much, much bigger than what Jupiter had to begin with. But yeah, we can discuss offline maybe. I don't know.
Yeah, and also I think the distance also will matter here. Probably when it is close,
I think
so
so.
the matter can actually condense in one object rather than be split across two.
Yeah, it's actually very interesting. Like, let's say if the Jupiter had become maybe we don't have enough time, but maybe we can discuss separately. Uh, let's say the Jupiter became a sun along with our sun, but then what will happen? It like in a binary, how does then all this two body problem, three body problems, and all? I don't know how it how it all pans out in when it comes to the orbits and all that. So it'll be interesting. It'll be very complicated,
Yeah,
in fact.
yeah. Let's continue, sir.
Yeah. So orbital resonance, I'll just show one small GIF image. So you can just watch for whenever these two planets come closer, the color changes to green. So this is basically the resonance. So when they come closer, these are massive objects, right? So as it comes closer, the gravitational pressure on both will be so much, it starts resonating at those close proximity. And this is basically what is happening when when the planets come closer. It is even visible. I mean, you can observe this in our day-to-day life as well. Like, when you are actually pushing somebody is sitting on a swing, and you're pushing that person so that the person swings, and as the person comes closer to you, you start pushing that person again. So after some time, it starts resonating how much the amplitude of this swing, and then the timing of the push, everything starts becoming resonant. And something similar happens when bodies like Jupiter and massive bodies like Jupiter and Saturn starts coming closer to each other. The orbit starts resonating. And this resonance actually has uh, different kinds of behavior in terms of it can cancel out each other, or it can actually change their orbits uh, in such a way that, like no, you would have noticed, like no, when this cloud collapsed and it started becoming a flat uh, shape, everything was actually rotating in a perfect circle around the proto sun. But when these planets formed, and when it started exerting gravity, when it starts coming closer to each other, it starts distorting its orbit, and it's sudden, what was a perfect circle can start becoming eccentric. It slightly can become slightly elliptical in nature. And that is what happened when Jupiter and Sun was coming closer to each other during their orbits. And this can result in unstable interaction. It can alter the each other's orbit in an orthogonal way, and it can exchange momentum and shift orbits until the resonance no longer exists. So it has a tendency to cancel itself out, so that resonance doesn't exist. A resonance system can also be self-correcting and thus become stable. So something like that happened when the Jupiter and Saturn was close to each other, and this had a big impact on other planets in the neighborhood. So if you look at this was proposed by a group of scientists in France, in Nice, in a place called Nice, and that's why it's called Nice model. And so in the initial stage, before Jupiter Saturn, it was a 2:1 resonance. That is, if when Jupiter makes one orbit, Saturn makes two orbits. So the 2:1 resonance. And so initially it was all like, in a in a perfect circle. It was all orbiting around the proto sun, and you had all those planetesimals around it. And then because the resonance, things started becoming slightly eccentric. You can see here the scattering of Kuiper belt objects into the solar system after the original left shift of Neptune. So because of this resonance, it started disturbing the equilibrium of the other planets' orbits, and it's things like the smaller icy objects started getting pushed out to the Kuiper belt area. And then finally, after ejection of Kuiper belt bodies by Jupiter, everything settled into the orbit that we all know in terms of the current eccentricity. Everything is pretty much stable right now. But initial days it was much more unstable. And a similar phenomena was happening in the asteroid belt as well. There is something called Kirkwood gaps. Kirkwood gaps are basically, uh, so if you look at this graph, this is basically the distance of the asteroids from Jupiter. So because Jupiter is such a big body, at certain distances, it starts exerting a resonance. And as a result, the asteroids in that area gets disturbed, the orbits gets disturbed because to maintain the resonance, to cancel out the resonance rather. And as a result, there are gaps in the asteroid belt. These are called Kirkwood gaps. And because of these asteroids getting dislodged from their original orbit, it starts colliding with other asteroids and it gets disintegrated. So probably that is one of the reasons why planets could not form in the asteroid belt, because it was moving in random direction because of the orbital resonance exerted by Jupiter on the asteroids. And the final stages. So all that happened. Now there is a period of late heavy bombardment. So 600 million years after the solar system was formed, Earth's water, the lot of icy bodies which were thrown out into the Kuiper belt because of this resonance that was happening between these four Jovian planets. Like earlier, what the study says is that Uranus and Neptune was slightly inner in the solar system, and it was thrown out into the outer regions. And because of all this shift in the orbits, the icy bodies were completely were thrown into disarray, and then many of them came pouring into the inner solar system. And this is called late heavy bombardment. And the water on Earth is believed to have come from all these icy bodies, which were uh, raining in from the outer reaches of the solar system into the inner solar system. And Kuiper belt we already discussed. Oort cloud is something interesting. As you all know, Oort cloud is more spherical. Kuiper belt is still maintaining the same orbital plane like other planets. but whereas Oort cloud is completely in all directions. So what the study says is that Oort cloud probably happened at the very end because of this resonance of these Jovian planets. Uh, some of the icy, not some, a lot of icy bodies were thrown into different directions, even in the perpendicular direction to the plane of the ecliptic, and as a result, it actually formed like a big ball. So that was the final stages in the evolution of the solar system. And this is just to summarize whatever I explained so far. Like year zero, when supernova or a supernovae, could be multiple supernovae, we don't know, triggers a collapse of a molecular cloud. That was about 4.56 billion years ago. And around 100,000 years after that, a planetesimal is formed. Then 10 million years, outer planets have formed. Around the same time, the Titori star was also formed, which is the first initial stage of the sun's evolution. Protoplanets in inner system and Titori winds sweep away gas and dust into the outer reaches. 100 million years, inner planets and moon form. 600 million years after the initial collapse, Jupiter and Saturn resonance happens. Outer planets migrate out. Asteroid belt depleted. Heavy bombardment happens, which brings water to Earth. 700 million years after, current stable configuration, first life on Earth forms. So that was a timeline summary. So this actually completes most of what I wanted to say. If time permits, I just want to spend a couple of more slides to explain something more interesting. I find this very fascinating, so I just want to spend some time, maybe 5-10 minutes. Any questions before I go into the next section?
I have one question. So, have you seen any evidence of any wood cloud kind of objects in other solar systems?
I don't know, Shah. Oort cloud itself is kind of nobody has proved the existence of it, though some of the long period comets believed to have come from inner part of the inner part of the Oort cloud, but I'm not sure about this. Maybe somebody
Okay.
else can answer this. I think I have few pictures following the slides. So this theory, it is actually we can see it happening, especially in Orion Nebula, and there are a few other places where some of these recent studies actually show this kind of planet formation. So it is possible that a similar kind of evolution can happen elsewhere. So yes, it's possible that out clouds can exist in other solar systems as well. It's possible,
Okay. Okay.
though
Yeah, I
there
think
is
we
no.
can continue the
Yeah, it's
discussion.
very difficult to detect them. They're such a small, tiny particles, right? It's very difficult. I mean, we couldn't detect our own Oort cloud. It's still theoretical, right? So seeing them in other parts of the galaxy, it'll be very, very difficult, I feel, unless they use some chemical spectroscopy and all that. Subsequent slides, because we're running out of time now. So this is just few pictures. I'm not going to spend much time. So this is Orion's dagger, and you can see those things that are blown up inside. Those are all basically star-forming regions. So you can see protosuns forming there, and the subsequent slide you can see more close-up. So this is basically disks of the molecular clouds with the sun at the protosun at the center. These planets are forming in the outer reaches. And in the next, this one, you can see this is Orion Nebula again, Orion molecular cloud. And there are so many protosuns forming in various different places all around the molecular cloud. So it's actually happening as we speak. This was recent means 3-4 years back. This was a big news. I don't know whether you have noticed it at that time. HL Tau. HL is again in the Taurus constellation. They could actually see this is actual photograph of a planetary system being formed. So it's a protoplanetary disk. The sun at the size at the center, and you can see there are some gaps in between. Those gaps, the dark lines, those are the orbits of the planets which are being formed. And wherever it is not dark, it is light, and that is where the icy bodies and gas and dust, everything is still existing, and then probably is getting accreted into forming bigger planets. Couple of unanswered questions. I don't know whether we have time for this, but there is still one question about we don't have iron 60 isotope anywhere in the solar system. Is either is absolutely no or very rare, whereas there is abundance of aluminum 26 isotope. But these two isotopes are available in equal measure in a supernova. So how come if it all happened through see see in a typical molecular cloud, it's basically helium and hydrogen, the initial from the initial Big Bang, right? But it requires a star to produce heavier elements, as you all know. So these isotopes and all probably like no supernova when it happened, it would have injected into the molecular cloud, which eventually collapsed to form planets. So why this is not present iron 60 isotope? I'm not going to explain because we don't have time. I will let you read later on. I can share the slides. So this is a new hypothesis about Wolf-Rayet stars. They say probably this actually the solar system was formed in a bubble that was like a bubble of a red giant or something, a star in its last days when it was expanding. The solar system was formed in that bubble, but it is still not proved. Scientists are still debating this particular theory. Number two is chondrules. uh, these chondrules, we don't know, for the chondrules to form, the temperature has to be much higher at a very short period. It should be a rapid increase in the temperature, and whether the compression of the gas would have created this much of temperature is still being debated. So that is the unanswered question number two. Sorry, I'm just speeding through this because we don't have time. Finally, the star stuff. Two things. So I'm not going to spend much time because you're all experienced amateur astronomers. So we all know that star is basically nothing but a fusion reactor which produces heavier elements through fusion. So when a star explodes in a supernova, it is actually ejecting all those heavy elements into the atmosphere, into the nearby neighboring surrounding areas, and as a result, when a molecular clouds collapse to form from a solar system or a planetary system, all these heavier elements are injected into the molecular cloud, and then whatever we talked about in terms of condensation and accretion of all these heavy elements, it's all borrowed from a star that was collapsed or burst into supernova, right? So stellar alchemy. So this again, I'm not going to go through it, but it's got some color coding in terms of each element from where it originated. If you look at those green, helium and hydrogen came from Big Bang fusion, and whereas things like lithiums and carbon, etc., are from dying of low mass stars. Then amber ones are exploding massive stars, and pink ones are cosmic ray fission, etc. So there are different origins of these elements. So this basically this chart or the periodic table very nicely explains from where these elements came. So my final thing is that what does all this mean? Like, no, if you look at our own genetic makeup, we are basically made of carbon. And recent studies says even our neurons require gold, right? So this gold has come from some other star. Gold is typically produced from a neutron star because it requires that much high, level of fusion and pressure, etc. And even whatever you heard me talking about in terms of accretion and all that, everything is come from some other stars. So basically, we are made of things from other stars. So basically, we are made of star stuff. So that is the main takeaway for me. Leaving the scientific aspects aside, if you look at or maybe if you want to call it as a spiritual aspect, or if you want to call it as a uh, non-scientific aspect of all this, is that we had to be kind, because we rose as phoenix from the ashes of other potential life forms that perished in a supernova. We don't know what kind of star was that. It had planets, it had life forms in it, right? So basically, we actually borrowed those ashes, and then we became what we are right now. So we had to be kind, and we had to be humble because our existence is by chance against odds. Um, so this whole process of planetary formation, probably Earth would not have existed if certain parameters of all this was different. Probably Earth never existed. So I have another. I was just talking to Vishwa before the start of this one. I have another small session I can deliver on how how life is able to sustain on Earth, right? So it's all against a lot of odds. So we had to be humble, and of course we had to be proud because we're all made of star stuff. That's all I had to say. Any final questions? I'm happy to take.
Saji,
Sure,
thank you very
that's
much.
my pleasure.
Wonderful session.
Thank you.
Thanks, Suresh.
Hello, am I audible?
Yeah.
Yep.
Yeah, I've got a question.
Yeah.
Yeah, so for you said there was a molecular cloud before all this, before the formation of a
Hmm.
solar system. So if it was
Yeah.
a molecular cloud, or if it was a supernova explosion, then there should have been some supernova remnant, right? Solar white dwarf, or
Yeah.
neutron.
So that's what I was saying. So yeah. So this molecular cloud predominantly had helium and hydrogen, which is basically the from the Big Bang, right?
Okay,
And so when supernova explodes, basically all the material that was formed through fusion, nuclear fusion within the star, gets ejected out into the space, and
okay,
that gets injected into the molecular cloud that is collapsing because this supernova probably would have happened in the immediate neighborhood of the molecular cloud. So all this heavy material, heavy elements gets injected into the collapsing molecular cloud. So that's why we are able to have at least some amount of heavy elements in the molecular cloud. But it
okay.
is still predominantly hydrogen and helium. But there is enough heavy elements to form planets. So it is,
That,
to answer your question, yes, these are all supernova remnant. That's what I'm saying. We're all made of material borrowed from a supernova.
Yeah, I hope Akash that answers your question. So, Desh, if you have any other question, do unmute yourself and go ahead and ask. Well, if there aren't any questions, then I think we can conclude this session. Once again, thanks Suresh for this wonderful session. It has been very insightful, and this session will be available in YouTube shortly. Do subscribe there, and you can watch it later.
Thank you, Vishwa. Thank you, BAS, and thank you all for participating and giving me an opportunity to share this. So I'm glad that it was useful and interesting for all of you. Thank you for your patient listening. Bye
Yeah.
for now.
Goodbye.